right? And for you, for me, for example, I already put it, look like here. For 4 point, look at 4 point. Here in matrix, distribution for 4. Okay, so you can go look like me, just specify the number of the point that you generate the matrix from. Okay, so again, homework. If I verify question in the final exam, so I pick up one kind of that, you compute the matrix for me for 2 point, 4 point. Okay, in programming design, okay, you have to write program to generate it, and also infer that also, right? Okay, you okay? Okay, that is answer at home, right? Remember, in university level, I deliver a design, but I don't have to score, right? For it in high school, okay, 50 minutes, 30 minutes, okay, 1 hour, and then some midterm and so on, right? But here we don't have time, right? So that's why, okay, I just deliver and then I check at the final. Okay, so that. And then for computation, okay, just multiply it, okay, the same. And one more, that is the inverse also, right? And the basic, you know, okay, the basic, you take the row down. You take the row here, and you get the row here, right? And you get the, okay, that's right. For 6 point, 15 point, so on, right? Okay. And for 2D, that is just 1D. And 2D, do you remember how to transform the form from image? How to? Transform from row and then get transform after that from column. And here the same, right? Here the same. The formula is the same. And okay, the advantage compare between here cosine, here for what is? You can remember one word is real number. Another energy compression. Okay, another keyword very important, energy compression. What does mean energy compression? What does it mean Vietnamese energy compression? What does it mean? Okay, what does it mean? And that is a keyword. Real, okay, you can see real. Then another energy compression. Why real? Because density is for compression. So first must be real, more effective than more efficient than compared to complex. Okay? Then energy compression means that you compress the energy of signal. What does it mean? You can see like that. You can see like that. Okay, figure here for 2D. Here the image. If you perform DCT and you get the output of DCT like that, so you can perform scaling, right? And you show, right? Because after perform, it's not image, so you have to transform to ray picture. And then you show that what does it mean? What does it mean? Energy compression. Look at the ball. Can you see what does mean the white value here? Very high value, right? What is dark value of black? Very low value, right? So energy compression means that after perform DCT, okay, the last value of FPM is just the correct corner. Okay, almost here is small, very small. That is very important. The perfect transformation if you want to remove a small area here, almost the energy is that almost large value. Okay, if you are able to reduce the size of what on the area of the large value, then we call energy compression. Why? For compression means that we call name. Okay, it's large, it is small. You just keep a small part here and you don't remove on the here, right? You just store on here. What does it mean? If you have image, original image like that is original image. And after compression, after density, you get the same sign, right? And furthermore, if only the area here is large value and here is 0, so otherwise you only store it, you shape it only. You don't see the value here. So the area here is small compared to the whole area, so that's why you shape the value. That is the idea of what? Of compression. You just store only. That is compression. So energy compression like that, right? Okay. That is what we call it for compression. So that's why, okay, I know I give you about the fundamental theory of DC by linear transformation, and then how to do it, just compression. And how to perform compression, because first, real number, that is energy compression. And the question is how, a little bit about how to perform compression, you can see here. But here I just for lecture of the image compression, but I don't get to keep inside this lecture to just show you more. Right, just show you more. So usually for energy for image, you have to divide into the block of 8 by 8 or 16 by 16, but almost 8 by 8. 8 for 8 block. You then perform the divide the image, the whole image into block of size 8 by 8. Okay? So you can see I remove for you about how to transform for 8 by 8 without 64 value only, right? Okay, I see. So here, for example, here I pick up the one block inside of that image. Here is 8 row, 8 column, one block, right? And in order to perform this thing, okay, and you have to here, okay, if I do transform, you can see on both probably long and here is small, right? You can see. Look at the ball. Right? Here, just very large, right? And you can see here is smaller, right? Very good. And now I will show you about that is the idea, but how in order to perform compression they have to do like that. They have to do like that. You can see. Here, I perform you the step by step of one block. A symbol here is the block measure from pick up from unit 64 value 8 by 8 block. Because it quick it only modified because the value of unit is from 0 to 55. So we shift to left, no center of 0, otherwise you get the value. Right? Because the magnitude is smaller compared to 255. That is the idea of that. After shifting, you get it? So you perform density. The density, you just transform density for row and then for column and then you get it. And you can see here, almost the volume is large molecules. And outside of here is smaller and smaller. You can see. And you also perform we call the quantization. Quantization, what do I mean? In Vietnamese we call the what does it mean? We just define the volume just for the one volume. And that quantization table, in that we divide for volume. And that volume only define this. Only define. How do we know? Because it becomes standard for image compression. Because we have to deduct it. You have, right? It's only the hair assisting particle. You just divide point by point. You get it? After you divide for one division, you can see, is spark volume, right? Almost is zero. Okay, you can see. And okay, you can see here, right? And now you just compress only this block of matrix of 4 okay. And you can see almost the volume here is zero. Except the corner, left corner. So how to perform compression? So you can see from this, you get the volume because it is 2D. You have to generate in 1D sequence. 1D sequence is just zigzag pattern without to get here or there. Right? We call zigzag pattern. You know zigzag pattern? Zigzag. After scanning what is zigzag, what I mean? You can see the sequence is shifting. You can see go down wall, go here 5, and go down here -5, and go straight here when one zigzag button. Okay? Can you know zigzag button?
Why don't we just say it's bad matrix? Why don't we just say the matrix is bad matrix? Notice all of the matrix is zero, so we can compress it up.
Okay, but before we compress, we have to linearize them. The input is the block SBS, right? You are from this state. Okay, you need perform this state. You get the block SBS. You perform that is quantization. You get also the block SBS. And after quantization, you can see almost of here contain volume and almost here is zero. How to perform compression? Then here we call zigzag. So zigzag, after zigzag, you get the sequence, 1D. And almost the volume here is not zero, and library along here is zero. Non-zero here. So now, in order to compress the matrix 2D, then now you try to compress here. That's the idea. That's the idea why you perform scanning. Because you want here 64 volume. Just in here you can see just different to zero and almost zero. Right? So that is now we have to perform encoding. Invariably we call mã hóa. So you can see in net here they have to use construction. What do I mean? Here they use this we call now another we call the intermediate representation here. What does it mean? You can see that the idea of that. Look at the wall. For example here, almost zero. Instead of storing the value by value, the idea of this is just because it's zero. How many zero? You just count how many zero, right? You just store how many zero and that value. That's the idea. For example here, just 1 8, right? 2 5, right? You did not to store 2 5, the value for 5 and 5, right? You 2 5. And similar here, for example here, but ending with 0, okay, value 1 2 3 a lot here. You can see you perform spark. No need to store, okay? One by form, right? We just count how many number? 0. How many number? 0. And that's only that's the idea of intermediate. And sure, from here you also some technique for image compression, okay? You get the sequence point. Sure, you have to use Hoffman also, right? And so that's why, okay, that is the idea of image compression. And what I want to call here, because we don't have a lecture on image compression or video compression, but what I want to call here is you have to generate the sequence of volume. The sequence of volume here at beginning just some volume different to 0, and almost here is 0. That is the idea. And how, for example, here let's say about 40 volume is 0. Let's just use 0 and 40. Okay, I did you 1 byte from and then also 1 byte from only 2 byte. No need to store a lot of value, right? Zero. That is the idea. But sure, you also have very specific on document coding also, right? To you to store the value. That is the idea.
Why we have to perform this task to transform two images to
Yeah, good idea, good question. How to get a lot of value in the same together? Because you have 2D, right? But how do you get the sequence of value in 0? What happens if it just flatten? You know flatten? Just concat line row by row. What happens? If you concat row by row, what happens? Why is that? You can see here. What happens if I just concat 0 row by row? Do I get a large number of zeros at the end? No. So that's why that is the idea of this. It becomes standard in the tree, right? It becomes standard. Almost all the background also they have to follow that idea. Okay? And then video encoder also follow that idea. So that's why is that? Why don't perform scanning? Just flatten. Because we cannot get the 0 to the end, right? If you just flatten. And so that is the idea. So for video, we also have very specific, but okay, here is just demonstration for how to use the DCT for compression. So again, the idea DCT for compression, okay. First, we call it real value. Next, we call it energy compression. Okay. Why energy compression? Because after perform the DCT compression, okay, and then you get it on more really long and here very small. And they also divide for the volume quantization table also, right? So it becomes very small like that after the division. Okay. So that is the idea of DCT. So I done the 2 lecture on frequency domain. Okay. Any question before our next lecture here? Get some minutes to discuss about Fourier and DCT. Sure, the very, very important application of DCT image and video compression on right now. Man, it becomes standard. So your homework is first on not on right now we study 2, right? Here is just linear compression. Okay, how to represent just matrix better. Let's see. The matrix better is just okay. You can see just before dot between row and row, right? It's define the similarity. So the what is different is just the matrix F here and here. Matrix W, right? But here is real, here is complex. Now, okay, if you don't have any questions, we go to the next topic is geometry. And what does mean the geometric transformation or transform? What does it mean? You can see in the application is sometimes you need to scale the image become smaller or larger. Sometimes you want to rotate the image, right? By angle. Yeah? Or sometimes you do the invert perspective, right? What does mean invert perspective? Okay, let's see. here. Easy.
Before we move to the next part,
Okay.
I don't really understand the effect of optimization in the density, how it affect the high frequency temperature or effect on the low frequency temperature so that it can break the temperature.
A good question. But why? If I hold on here. Okay. I back to the no, here. Look at the ball. What happened? You asked me about what is the effect of the quantization. Okay, so I showed you about the after DGT. What do you have? So you can see here is what the DGT the result for what SBS in 64 value. It is put here after. Just transform this for all column together, right? And because what you can see that is already, this is only energy compared to the left top corner. The magnitude is long, magnitude only very long, right? And you can see for this one becomes smaller, so smaller. You show that? But they who researcher, they want, okay, because it's not here, right? And they also different. They want to go further, okay? So that's why they propose the quantization table, okay? The design already for you. The quantization table also SBS value, okay? As so before, you just division element wise only. Right? Because you have table, quantization table, you take the table here, you divide the element one, and that element by element. You get it. Okay? You round to in, you get it? Why? Because they won't go further. You make here in order to perform compression efficiently, you must have after this, you must have sequence values the same. And now zero. So if you plot them here arbitrarily, if you perform this from here, you can see the value is not the same. They similar, for example here they are more similar without the difference is just within the some brand, right? Similar, but not the same. So we are not able to perform encoding. Look like 40 value 0, I just store 2 right value, the number and also the actual, the magnitude of it. You understand what I mean? The idea of compression right now is if you have 5, right? 5 value in 1, right? I said you just store 5, the just 1 and magnitude in 1. That is the idea. So if you perform this from here, you cannot get the same values to get sequence. But you perform foundation, you can see on what is here and on what is the same, right? You can perform this and you can see you have the sequence value the same, right? Sequence very long or very long sequence, right, with the same value. Okay, that is the idea of quantization table. So research, they have to design the table already. Here table. Sorry, here table for. It becomes the industry standard. So that's why you just find quantization table, right, for image, okay, and then you get that, right? And for you divide element by element. Is it okay? Just idea. Any question more? I give you about the meaning of compression, but the lecture on image compression all have been removed from this semester, some semester only. Because now we just move into the learning, right? So that's why I did. And actually, in industry, almost the user use the API only for image decompression. That's even I don't know, right? Inside how this is.
So the quantized table just has side
Now it's standard EAPS or 16 by 60. Now the standard video compression right now is 64 by 64. Right?
So if our size is like different from the size of the quantized table, so
You also have a quantization table.
Sure,
because they propose they have to use it. But the question is, do you know why they have to, the whole image they have to perform into block of FPS or 16 by 16? Do you know why? Okay, that belongs to the image compression. But let's think about it. Why why they don't perform the DT for the whole image? Well, but they have to perform into the FPS or, for example, check it right now is FPS. Do you know why? Because they encode the block by block independently. So when transmission, if during transmission is just one block, you get error, and then the whole image, you can see, sometimes you see the television, you can see there are some blocks the same color, that is their error. And it's for whether it's not so good. So you can see the block and very small is the same, because that is error. So they just be by the same color. Now we go to the transformation. Okay, let's talk about application of that. Okay, we go about. Let's talk about I want to talk about perspective first. Can you see it here? Why wrong? Okay, can you see my screen on this? First of all, I draw here, that is the whole image. And my screen look like this. Okay, my screen. And if I want to A, B, C, D. I insert a picture here, and then I saw my screen look like the flat like that, and we call the inverse perspective. Right? So a lot of application in real life. For example, if you train the deep learning model, one for image production, for image application. So the data augmentation means that làm giàu dữ liệu is computer task. You have to perform that. In order to perform the Sure, you also you elaborate, right? But okay, they remind you about area of scaling, rotation, perspective, and so on, right? And we study about how to work inside. How to work inside. You study how to work inside, but actually in real life, okay, you should do ABI, for example, Imperial, data, augmentation, Imperial, transformation. The question is how to perform rotation. You get you have to use matrix 3 by 3, and what does it mean? How to transform? Look at it. Now you have a concept called homo. For the image like that, you have y. That is 0, 0. You know all this, right? And for pixel A, so you have A, that is AF, AY, right? You know that, right? AF, here AY, right? On what of you know? Look at the ball. The difference here is now what they mean homo system or homo coordinate. Here is the point 2D. Right now we are turning to 3D. You pass one here. So here is representation of point A in homo system or homo coordinate. Okay? 3D, not 2D. Please focus on the whole. Homo. The question is, what is application or what is the advantage of homo representation? What is the advantage? The advantage is one kind of transformation geometry, just linear transformation. Good. Again, you can see when I represent the new coordinate, right? And it becomes the homo representation. And what is the advantage? Why? Why? Because you can see scaling, translation, rotation, shearing in all kind of transformation. Even the rotated is just linear. You just multiply matrix and vector. That is application. You do not have to. For the before that, for example, if translation, if you don't have, what happens if you don't use homo? If you don't use homo, right? If you don't use homo, A equal to AF, AY. I translate by BF dy. So AF equal to AF plus DF. AY equal to AY plus dy. You have to perform addition. You have to perform addition. Right? For rotation or scaling, you have to perform multiplication. For example, you can see if here translate, here for rotation. That theta, right? Theta degree. Then you can see IS from equal to cosine of theta multi AF plus subtract sine theta. Okay. So you can see, in order to translation, you have to perform addition. In order to rotation, you have to perform multiplication and also addition. Come that right? anything. What happens if I represent the point in homosystem and how to? So matrix for translation equal to okay over there. Yeah. Right? So you can see A1, 1, 1, dx, dy, 0, 0, 0, 0, and you multiply with f, ay, 1. What is the result here? Right? And here is 1. So you can see translation right now we just multiply between matrix and vector. And you can see matrix and over there you can see for rotation also. For rotation. So you also have equal to MR multiplied with. So that's all. And even all kind of geometry. So that is application of homology. Okay.
I want to see the meaning of what does it mean?
We introduce that because when we introduce that and then we unite right all kind of geometry into linear transformation. So that is the idea of design system. You have to design like that, right? To unite them into that. Okay, you have to design. That is the idea.
Does it mean the distance between the projector and the screen? So image.
The same. After transformation, you forgot this value, but you throw it away. That's value. Okay, that is just one kind of representation. And usually for homosystem, for affine transformation. So what does mean affine transformation? In Vietnamese, affine is just affine, because we don't add the meaning in Vietnamese. Okay, so we know the affine. Okay, we know that, right? So what does mean affine transformation in theory? Here, it consists 6 value different to 0, right? Different 3 value. You have to change, you have to learn okay 6. So if you did only fit 0, 0, 1 here, we call affine matrix or affine transformation. 6 degree of freedom. DOF, degree of freedom. 6 degree of freedom we call 6 bậc tự do, mean that 6 only. You have to determine 6. And you can see all kind of affine, and then after that, the result here is always 1 here. Only 1, you can set it. You can verify that affine. And what does it mean? Perspective. For thiết mặt cái gì này nào ý? How many value? Actually 9 value, but because if it's here you can divide from here only 1, so there is only S. So affine perspective is just S degree of freedom, not S value different. You can choose to read. And when you multiply with for the ball, the motion and P multiply with for P equal to Pf, Py 1. So what is the PIF? We don't care here, but what is the value here? I don't care that right? But can you write the value matrix MP with letter P here? A31 multiplied what? Pf plus A32 Py. And plus 1. Here is may be different to 0. Different to 1. So after positive transformation, you get the new point or image point is the last component is not different to 0 to 1. So that's why how to convert to 1. So that is F that is y, that is w, right? So that is equal to u divide. So actually, that is the coordinate in 2D system. After transforming here in coordinate in 2D system. From okay. What I mean? I tell you the way to represent 2D into homo. Just introduce just one, okay? That's one. From homo s y w into 2D to divide 4w. That's right. Okay, that's why you have to know about the. Wait a minute, what I mean homogeneous? What I mean homogeneous mean? In Vietnamese. Meaning of homogeneous, what I mean? In Vietnamese. And the question is, why, first of all, if you study in C, maybe C, also you have one called parallel computing or maybe another called similar called optimization, right? So they learn the technique to accelerate the computation of matrix and matrix multiplication. Why? So if you have the knowledge in real life, you went to the study that course. Oh, matrix and matrix multiplication, okay, in linear algebra you know how to learn, how to multiply, and then now optimize units, right? But actually you can see, okay, geometric transformation is train out just matrix and matrix. And in deep learning you have linear layer, right? Also matrix and matrix. Okay? And for the computer office, okay, you also transform the point, right? A lot of point, million of point, that's it. Also matrix by matrix multiplication. So you can see matrix and matrix multiplication is very popular in scientific computing. Okay, now again, even for transform and also leukocyte transform, you also matrix transform, right? I give you about that. So the question is right now, look at the ball. Your task maybe in final idea, the question is, can you write a matrix for replace the image, or we call horizontal flip? Okay, for example, do you know that before? In real. Okay, how to write a matrix here? What is the matrix? What is the matrix of vertical flip? Right? Because it's also geometry, so it's transformed by the equation. So how can it be? How can? Do you know what I mean? Okay? Because it's geometry, it's just like it, and then you have to do it. So example, for you prepare for yourself. If I ask you in final, okay, write a matrix for horizontal flip or vertical flip or scaling or shearing, so on, right? You ready? You ready? Do you know my question? And transformation is simple, right? Right now, okay, I give you the rule of how, okay, the guideline. Some matrix is very simple, you just write directly, no need to do something, right? But some, you have to follow that scheme. Furthermore, how I give you about how to find rotation matrix, and to give the same idea to find order matrix, right? You know what I mean? So input that part. I know input without I give you x and y. And also x prime, y prime. Okay? I give you find matrix for me, rotation. Or find matrix for me, right? How to? Do you know what I mean? I give you x, y given. X, y, and also x prime, y prime. Okay, question? Method. How? So you can see, if I assume that I accept that, if I assume that here is rotation, I say well, then I write relation between F prime to the angle here, right? I assume that rotation. And you can see I decompose it there. Right. So for example, if you have a relationship between the output point with what we call the destination point of X and Y referred to the input, the source point of the X and Y. If you know relation like that, right? And now I think that rotation you can find. But if for relation, reflection or scaling, okay, you do the same. You must find relation between F prime to input point F1 and similar for Y prime. And now you can see, you know, 3 by 3, okay? Geometry is very general, 3 by 3. Okay? So why how to? You take multiply by symbol, you get relation. Right? And now, if you identical into that, you can find A1 and A2. Can you? Yes. Can you what I mean? You multiply symbol, you get those equations. If they give you about X, Y, right, and over here, and then can you find the A value, A here, A actually, you are able to find. Find rotation, how to find rotation. What are it can be one. If you have relation between right, then how to? How I get the A11, A12, the matrix like that? Do you know what I mean? Why? Look at the board. Okay, the output in matrix, how do I generate matrix like that? If I have relation here, if I have relation F to F1, but how can I generate matrix like that? Look at the board. You should matching, right? You should perform matching, and you can see here A11 would be equal to now, A12 would be equal to that, right? If you write relation between output and input point, then you easy to identify. For example, if you give like that, because you have relation between output and input. Okay, let's talk about how to identify. Okay, similar. Stop here, right? Do similar exercise. This is in matrix or horizontal flip. Do it for me. Horizontal flip.
If we still use this system.
Here is just an example for rotation. To find relation between F prime to F1. Okay? The same, the principle is the same.
How about translation?
The same. Here is theory method, and here is just minor different. Okay, we can do that very different. Okay, so then, what is input output? The image là F, the Y, the image here, right? So here W and here is H, right? Mean up W mean up from 0 to minus 1. Here W, here H. W mean up the width, mean up the number of column. H means number of row. Mean up the index from 0 to here is W minus 1. Right? Here H of 1. Holding complete. So one for here, S and Y. So S, Y, you make into what? Y is the same. We talk beautiful. Y is S. Minus S. No, we call it. But even mất gì here? Mất gì tới tiếp?
W minus S.
Minus S plus what?
W. W.
Plus W. So you have to verify for me. 0, 0 here, map to what? 0 here. After flip, what? Map to what? Map to W minus 1. Right? So 0, 0, 0 here, map to W minus 1 now, right? It's 0. Map to 0, okay? W no. Impossible. And we W and get up.
Plus 1.
You have to perform calibration without calibration for border value. Border value you just correct. For example, 0, 0 here. After flip, what is in the direction? Mới đã bỏ right. That point, what is it? W minus 1 and 0. And 0, 0 must map to that. So you verify 0 here, W is in front. So how to walk? I'm not 1. Why we come here, right? You verify. So you have relationship S, right? Here you got F prime, here is Y prime. So F prime equal to, right, minus S, subtract for W minus 1. Y prime equal to 1. You have 2 here. Can you identify for me matrix like that? M equal to A11. Oh, tell me about that. A11 equal how many? Minus 1. Here, minus 1, right? A12.
0.
0. A13.
W minus 1.
W minus 1. Here. 0, here. 1, here. 0, here.
0, 0, 1.
Okay. Here. Now you have to perform like that, and you have to move the input, the output will be within the range 20 like that. You have to. If for example, river can be about just minus S, so impossible because we don't have the connect minus S, right? Okay, so why you have to. Actually, it's comparison of 2 transformations. That is first, replace and translation. Can you verify? It is okay. And similar for order at the time. Find for me vertical, shearing, and whatever. Again, the most important you have to find relationship between output and input. If you have relationship, you can perform identification. Okay? You get it? It is okay? Now, how to find matrix to transform from here to here? To get, you hold the same set to that. And you also do it in exercise, drawing exercise. Drawing exercise, you just capture a picture any here, right? And then you put here, and then you make into the output here, generating the form. The question is how matrix. Okay, similar for showing, okay, whatever I skip, right? I skip, is it okay? I skip for exercise. Now I go to the for perspective estimation. How to find a matrix? Whatever if I give you about A input, A to A, B to C to D to, I give you the coordinate of A prime, B prime I give you. Right? I give you. So for example, A, B, C, D easy because you just point then you get the coordinate. What is the coordinate of A, B? A prime, B prime, C prime, D prime, A, B, C. How you get it? A maybe here 0, 0, A prime 0, 0, B whatever, B prime whatever you want, right? C prime whatever you want, B prime whatever you want, right? But if you want to see the picture clearly, look like here. Do you know what is the ratio of that secret? This secret, what is the ratio of original value? There are two popular values only. Do you remember the ratio? Immediately what I mean? Tỷ lệ màn hình, right? What I mean ratio here? Maybe 40 or 69, right? You know popular?
Yes.
Here is 40 or 59? 40. So if you want the picture look like here, after perform invert the perspective, you must use the ratio the same here. For example here, A you must use AB prime, C prime, D prime, whatever. But must satisfy condition here is A prime D prime divide for A prime D prime equal to 40. Then you see exact the picture of it, right? Do you know what I mean? If you change different, then you might be distortion. Okay? So you give again, you give another input and output is the matrix for me. Matrix for me. How to derive matrix? If I give you about the coordinate of xy and x prime and y prime, I give you and xy also give you, then you have to define aij. Aij without the matrix. How to? You make the equation like that. Just one pair, right? One pair, you get like that. And similar like that. And similar like that, right? Pair that is the truth arrange value and then put the value there. And just one pair you have two equations, right? One pair you have two equations. How many values do you want? How many variables do you want to determine? A value, right? So you have to make A equation. At least A equation. So you have 1 point, you get it? 1 point, you get it? One pair, you get it? So you have at least 4 pairs because 1 pair generates 2 equations. 4 generate 8 equations. But many more okay. So you have pair 1, pair 2, pair 4. You get it? Okay, right now you have what you have because I give you about a pair. If that you have this matrix, you have this vector. You need to find this vector. So you have to solve linear equation, right? You have to solve linear equation, right? So I call A that is matrix. S is contain the S value to find vector, and you have B that is the vector. You have it. How to solve it? Remember here is no missing. at least 4 pair, but you have maybe 5, 6, whatever, right? So but one pair generate 2, n pair generate 2n, right? So here you have to solve by pseudo inverse. Then what do we pseudo inverse? Giả đảo. Why? Because matrix A now is okay, impossible to inverse because it's not square. So how to do this? It's very popular in linear algebra. You multiply with 18 to 1. You get it? And here it becomes linear. Becomes square. You have to take inverse. And you have to get the value test like that. That's all. Here and so on. You have to do this. Okay? Matrix now is A, right? In NumPy, how to perform inverse on matrix? NumPy dot linear algebra dot IVF, INV, right? So you get it. Okay, so okay, I know now I finished your exercise how to write matrix for popular scale, rotation, flipping, so on, right? Or if I give you relation between input and output like that, you have to generate the matrix, right? That is simple, right? And more, in order to determine the very zero matrix coefficient, you have to use tensor like that. And homework, see the picture here for me, and you have to generate that form whatever. Flip. Now, write program to generate the picture A prime here for me. So that. Programming exercise. Now, I give you about, okay, first, by using homogeneous system, you have to unite all kind of geometric transform by linear. I give you about how to determine matrix FW, right? Now how to perform transformation. As it gives how to perform transformation. You can see how to perform transformation. You can see here. First, you have to method backward and forward. What is backward? What is forward? Do it forward. Okay, actually we have to be backward, not forward. Why? Because forward you have to have Howley effect. You can see that here. Going forward, because you want to generate image, right? And if you for each pixel in source, and here is source, here is definition. Here is source, and move. That definition is 100, right? For each pixel in source, you compute the coordinate and you copy the pixel, right? Like that. That is good. And you get Howley effect. Howley effect here. Do you know why Howley effect? Why is case hold like that? Because you have your element for each pixel in source. You determine the coordinate on the data stream and you copy the intensity, right? It's not forward on the pixel on the definition, otherwise it can go. So forward it cannot be used. You should use backward. Backward, how to do backward? For each pixel in definition, for each pixel, so you have to fill on color for each pixel. You compute the corresponding pixel in source, and then you copy the intensity. That's the idea we call backward. Backward, I mean, why we call backward, why we call forward? Đường nói source and destination, right? Here on P, you map into here on P prime. So P prime is equal to matrix M multiplied P. So how to get matrix P? So P infer P equal to right? So you can see forward, backward, okay. So the question of backward Remember, because you had to form a for episode in definition. You determine the coordinate here, and then you copy the intensity. That is the idea, right? And the question is, after you compute the coordinate by the equation, so the coordinate here is -1 multiplied p prime, real value, not integer, right? Real, right? So that's why you need interpolation, right? Because what is the coordinate of this one? 0, 1, 2, 3, right? So that's why you need the interpolation. So you have interpolation like that, right? That idea. Zero order. What is zero order? A zero order because you just round the coordinate only. Zero order. Or we call nearest. In Ipcv or many libraries, they call nearest. Gần nhất. After you round to nearest pixel. Okay? And here is bilinear. Bilinear, you have to have the input. Okay? Here that is the intensity of source, intensity of source. You multiply the in bilinear. Right. And then there is cubic. You have to perform the equation interpolation here. Cubic. Okay, so that's why I give you about 3 equations in formula. And sure, nearest is fast, but not so good output. Cubic, very high quality, but very slow. And usually by default, reasonable should use by cubic, by linear. Is it okay? Yes. So I am very good. So I give you about example. Coding. You also have coding like programming. For the phone, you have 2 images like that. For the rotation, here translation, here scaling, here steering matrix. You define a matrix here. Translation, scaling you can see. Scaling, rotation, what kind, right? Printing so on, right? And then you perform backward for me. Okay, you can see backward. Can you see any follow? I told you that in theory, for episode in definition, you compute the coordinate potential. But can you see follow right now? No. Why? Because I use the vectorization in the time, right? So you do similar, don't try to use. Okay, for me, you can see one more correlation. Output multiply with here. You get a short definition input. I see multiply that. And how to get the coordinate of input output? You can see I made the addition how to make it output. Okay. I give also the no, not M. Here, what do you mean here? Can you get it? For episode is definition, right? Okay, I generate the pistol on or the pistol in definition image into the array level. Okay. I collect all the pistol into the data in matrix. Matrix that is look like how many row, how many column. Here S, here Y, here 1, right? So can you tell me how many vectors are there? How many rows? 3 columns, right? S1, but how many rows? Is the matrix N row, S row, 3 columns, right? Okay. You know what I mean? You need long to follow. Very slow. You have to use that. Okay, that is just multiply with transformation. So furthermore, okay, you had it. The question is now rotation, first rotation. When talking about rotation, where is the center of rotation? Let's talk about rotation matrix. Okay, rotation matrix. What is when I rotate the image, right? So rotate. What is the center of rotation? What is center? One center. If you have image like that, you why? When rotation is rotation by default at this point. That's what? To the right. Default. And rotation 45 degrees. What is 45 degrees? Look at the ball because you can know what is 45. Usually 45 degrees like that, right? In this direction. 45. But right now you just to be at what is it? What is 45? 45 degrees here. Okay, here come. Here is positive. You ask me about that question. So okay, that is about. Now my question is by scaling, you also scaling right back to here. So what happens if I want to perform rotation with center P, center C here? How to? Because by default, any matrix rotation is rotate around here, right? But now you want rotation around here. How? Translate, letter here, right? And letter D. Translate and then translate, left, okay, and rotate and translate that. What? Okay, that's it. So here is just the input and output the same sign. Same sign, right? You do like that. But the input and output different design how to do. Okay? They different too. Okay, here remember for input and output the same sign, right? You have to view it. So again, so if again we talk about inversion is easy when you can machine. You can unify, right? Because unify the linear variable dot IMB, you have it, right? But in paper where I don't think you can perform inversion right, fast, right? So you have, if you give receive a question like that, but you trick it. Okay, what I mean? So if you want again for property, if you have A, B, C, D, E inverse equal to how? That is equal to D inverse, C inverse, D inverse, then next. If A is just scaling, so AS minus 1 equal how many? If you scale by S and this one, right? Now how to perform inverse of that? One of SS, SY, then inverse equal to 1 over SS, 1 over SY. If you have MT of ds dy, how to perform inverse? but dx minus dy very simple. If MR is of alpha, how to MR rotation minus 1? How many here? Minus 1. Okay? No. Okay, again, one, because I don't think you have you can compute half, right? So very tricky. So you can see you write around for me about it. Right here. So you can see, if the input set and output set different, right? Then you cannot give t minus 1 RT. Remember t agent, remember the vector from here to here. The vector from C, again, vector C to O. Vector D, right? D from CO, right? Equal to O to successive, right? O to successive. So remember that. Remember about how to talk about translation in this direction. Vector D. So that is equal to. Now, what happens if you rotate alpha with input and output difference R2? You can see how defined. And into our data from source to potentially equal to MT, the number of rise effort, acceleration, rotation, scaling, and also MT2. So MT, you can see MT, acceleration like this. Acceleration is MT2, what MR, MS, scaling like this, then Y, right? And it equal to the ratio of output to input, right? Can you see it? And what does mean the MRT multiplied by dx multiplied d1. Can you give that one? Okay? Can you? So your home will be determined that. Because I write from here now paper can. Paper can how to determine the portable. If I give you about that, right? If I given the input image portable, the input image is 200, the output image is 600 by 600, right? Not only you cannot use only that is simple, right? If like that, then the output is the same time. But right now, output is bigger. So you can see SS and Y equal to 3, right? Y 3, 6. Yeah, 6, yeah, right? So the question is how to determine the matrix for acceleration right now. The question is Y. Okay? So matrix here is MT what? MT, MR, MF, MT2, right? Okay, different. How to do? Why not it? Scaling, okay, easy. But maybe you do in the frequency domain, okay? The case line here. But before come to here, in frequency domain, any question about it? So you are not surprised if I had a question here, given the image is 200 inputs is short, and that is really 600 output. I want like that, right? And I want to rotate the image here at some point, right? Okay, how to write deterministic. Yeah. And that question maybe I ask you about the point. Some point here is what is the where I see in the output, right? Or some point here what is where is correspond to what, right? You say what I mean? I don't know. So any question about it? We nearly complete the lecture. Nearly complete. What did it? Right. Okay, next. There are some photo, can you see the effect on it? Look at the ball. Can you see why you have some kind of effect? Look at the ball. What happened if on point at y in that direction because you perform backward mapping, right? Means the point is in that direction is that is for each valid point. But when you map it's outside of each other, invalid, right? For the which sample here, how to get body. Maybe you copy, you round into the border, right? Or whatever, right? You can see. That's all that one had effect on it. Or you can do only scaling. Now you only scaling, right? So special for scaling. So you have to perform in Fourier transform. Okay? In this order. But now also one we call the polar transform. For example here, I want to generate a picture around here to here. Polar, how to? You know what I mean? Polar. Look at the draw the straight line from here, away from here, and then just draw around it to the center, and then you get the picture. That's the idea. Because sometimes you want to get the picture like that, right? How to? Here. So you can see you have R and theta. Here you are. Here theta. Right? So you have to perform radarize without you define to the cell like you do like radarize. Because R and theta are theoretically real, but you have to sample, right? And then you get the cell. And then you transform back into the body push. Is it okay? So that's the idea. So I want to close the lecture right now. So today is the lecture number 5.
Yes.
Right? A half of our program reserved for deep learning. Without the classification, segmentation, addition, deep learning. So that's why we have one more lecture in top transform. in the slide, you have to read it for me about also do exercise on this or half plan form. Half plan form. Right? And then the other is just for neural network, and then also classification, segmentation, and so on, right? Is it okay?
Yeah.
So read it before. So in this course we don't have the midterm, right? We don't have the midterm, but I also release some exercise for you, alright, to do similar like that, to check. Because if don't have any activity like that, then maybe the final will fail. Because I give you a lot of exercise, but not scoring, right? So that's why I'm sure you are lazy. So when I give you exercise, please do it at home. Maybe some exercise in the final, right? Because you can see we study here. You study with me 30 hours only, so we don't have time to do so, right? In Europe here, so please do. So I give you exercise, growing exercise. You also do it at home. Without that, maybe you fail the final exam. So any questions before I close the lecture? Any questions? No, right? So see you next week.